Today we'll talk about what produce magnetic fields. Okay? So all classical electromagnetic phenomena are described by these 5 equations. These 4 equations are called the Maxwell's equations. Okay. What these equations tell you is these are the causes on the right hand side, and these are the effects. Okay, so this equation tells you that charges produce electric fields. What this equation is telling you is, okay, so one of the things this equation tells you is you can buy positive and negative charges by themselves, but you can never buy a magnet with a north pole. You can never buy a north pole of a magnet by itself or a south pole. Okay? They always come in pairs. This equation tells you time-varying magnetic fields produce electric fields. This equation tells you currents, moving charges produce magnetic fields. Also, time-varying electric fields produce magnetic fields. And this equation tells you, all right, you produced all of this stuff, electric and magnetic fields. Okay. This equation tells you what is the effect of those electric and magnetic fields. Okay. So the electric field will exert a force on a charged particle, and a magnetic field will exert a force on a moving charged particle. Okay. So between these equations, you cover all of electromagnetic phenomena. So if you become an electrical engineer, you'd be very familiar with these guys. Yeah. Today we're going to talk about this half of the equation. We're going to talk about currents. J is the current density, moving charges producing magnetic fields. In one of the later chapters, we'll talk about this guy producing magnetic fields. Okay. All right. Now, the form of the equation tells you the configuration of stuff. Okay, so for instance, this equation is telling you that if you have an infinitely long straight conductor carrying a current I, okay, the magnetic field around this conductor forms concentric circles. Okay, so magnetic field.
Current has a magnetic field around it. The field lies in a plane perpendicular to the.
Okay. Magnetic fields form concentric circles around it. So that's what this form of this equation is telling you. Okay. And the magnetic field is I'm drawing a blank. I mu naught I over 2 pi r. R is this distance. All right, so that's what's going on. Okay, that's what this chapter is about. Currents producing magnetic fields, and we'll give you some configurations where the magnetic field, we can give you a formula for the magnetic field. This is the easiest case. Okay, and okay, so here's another deal. So will this wire produce a magnetic field?
Yes.
All around it, okay, all the way to infinity, but we don't have a formula for it. Okay, I can't tell you what the magnetic field is there and stuff like that. If this was a straight conductor, then I can give you the expression. Okay. All right, so that's what this chapter is about. Currents producing magnetic fields. All right. So now let's go through the slides. Okay, so here's a big boy toy. You can see the dimensions of this. This is roughly the size of this room. And what this can do is this can exert a force of 5 million pounds on an object. And it can give you escape velocity in a few milliseconds. So you fire an object, and it will go to space. Of course, you can't fire astronauts from this, because if you fire an astronaut from this machine, what you'll get is a pellet reaching space. Okay, you'd get crushed. So anyway, so this is called a magnetic gun. Okay, so this is for launching payloads into space using magnetic forces. Of course, the payload can be only a solid object or something like that, because anything else would get crushed. Accelerations of 5 million Gs. Okay, so that's a force of 5 times the object's weight, 5 million times the object's weight. That's the kind of forces you can exert on this. Okay. And by the way, so acceleration for about 1 millisecond. So you're going from 0 to 10 kilometers per second in 1 millisecond. So how does this work? Okay, so here are the rails. There's the projectile. There is a fuse. Okay, and what the fuse does is, what happens to the fuse is, if you pass a large current through the fuse, it instantly vaporizes. Okay. Remember, all this is happening within within a millisecond. All right, so so in this chapter you learn, okay, where did we go? Okay, so here was the current. There was a current that's producing this magnetic field, and here is the right-hand rule to figure out the direction of the magnetic field. Stick your thumb out in the direction of the current, and your fingers point in the direction of the magnetic field. Okay. So let's go back to this guy. So what we'll do is we'll pass a large current through this thing, and the large current can be up to, well, thousands of amps. Okay. So this current will vaporize this fuse instantly, and it produces this magnetic field into the sheet. Stick your fingers out, and the magnetic field is like that. Okay, so the magnetic field is into the sheet. Okay. Now this vaporized, so this has become plasma, positive and negative charges. So now let's just look at positive charges. There's a positive charge moving in this direction. Okay. The magnetic field is into the sheet. The force on the charge, on that positive charge, will be QV cross B. V cross B, the force will be upward. The force on that charge will be upward. And that's what's pushing this projectile. Okay. And like I said, 5 million Gs. Must be spectacular to see. All right, so we're talking about this half of the equation today. Okay. So what is it that we're saying? We're saying that moving charges are going to produce magnetic fields. Okay. Now, everything we talk about really relates to, we're talking magnetostatics. Yeah, so the subject, but okay, so the currents have been flowing for a long time. They're steady, they're not time dependent. The magnetic field here is only spatially dependent. If this became time dependent, this would become time dependent. but we're not going to do that. Okay? So we're just talking steady state. Okay? Well, this current is what's producing the magnetic field. What is current? A bunch of charges moving. Okay? So, but this current has been steady, so you've been having the stream of charges flowing forever. Okay? So what we're going to say is this field is the sum of the fields produced by each of these charges. Okay? And so now we're going to tell you what is the field produced by this one charge, single charge. Okay? And what is the total field? It's the field due to all of those guys. Okay? So that's the background going on. Okay? So the reason I say this is, okay, we'll give you the field for this one charge, but that's not really true. That's true only in that context that I mentioned. Okay? All right. So we don't have to worry about all of that. We'll just take this as true. Okay? Okay, so here is a positive charge moving in this direction. And this is how the field it produces. So stick your thumb out in the direction of the charge, and your fingers point in the direction of the field. Okay? So what you can do is you can take a cylinder. Okay? The charge is moving through an axis of the cylinder. Okay? And the field is tangent to the cylinder, perpendicular to the axis. So this charge is producing a field everywhere. Okay, if it was part of that train that has been going on forever. Okay? And the further out you are, the weaker the field gets. So that's the configuration. Okay, of course. So now you know the basics. If you get the charge moving the other way, the field is pointing this way. All right. All right. So here the charge is moving this way, and there's the field. And the further out you are, the weaker the field gets. Okay. This field here is there. Okay. What this diagram is showing you is an end-on view. So the charge is moving into the plane, and there are the field lines, concentric field lines. The field is stronger here, weaker there. Okay. All right, so here is the formula, basic formula. The field produced by this moving charge at that point, okay, so there is the field, magnetic field vector, and it's given by this expression. All right, mu naught is the vacuum permeability, and that's its value, 4 pi times 10 to the minus 7 Tesla meter per amp. Q is the charge, V is the velocity of the charge, cross r hat. What is r hat?
R unit vector.
It's a unit vector in the direction of the point at which you're calculating the magnetic field. All right, divided by r squared. R squared is the distance to the point. Okay. What happened? Okay, r is the distance to that point. All right, so now let's look at this equation a little closely. Okay. Do you guys remember what is the cross product of two vectors that are parallel to each other?
0.
0. So if two vectors are parallel to each other, the cross product is 0. If two vectors are anti-parallel to each other, the cross product is
0.
0. Okay, so that's the first thing we'll notice. If V and r hat are parallel to each other, so if the cross product will be 0. So this moving charge doesn't produce any magnetic field along the axis along which it's moving. Okay? Of course, the simple fact is if Q is 0, if it's uncharged, it won't produce any magnetic field. But we started off by saying that you have to have a charged particle that is moving to produce magnetic field. R square, the strength of the field falls off as r squared. You go twice as far, and the field strength is 1/4 as much. Okay? All right, so those are the things you want to notice about this. All right, now that we know how to calculate the field for a charge, what do? We just get a bunch of charges moving. Okay. So here we go. Here's a wire with a current flowing in it. That's a bunch of charges. Let's find the field due to the charges flowing in this piece of the wire. Okay. So the field due to the charges in this piece of wire moving is given by this. dB is mu naught over 4 pi I ds. There's ds. Okay. So ds is this vector cross r hat divided by r squared. Okay. So this tells you, okay, so what does this term include? It includes n, the number of charges moving in that element, times the charge of each guy, times the velocity of each guy. Okay? So all that is all this guy is n times that. Okay? So you added the fields of all those charges. Why could you add it so simply? Because the field produced by each charge was in the same direction. Okay? So, and it was in the same direction and the same magnitude. So, okay. All right, so that's why we could do it so easily. All right, so we know the charge, we know the field produced by this guy, by these charges at this point. And what is the direction of the field at this point? I'm sorry?
Perpendicular to the current?
It's coming out of the sheet of the paper at this point, okay? What would be the field here? Stick your thumb out in the dirt. It would be going into, okay? So at all these points, the field is coming out, and all these points, the field is going in, okay? All right, now you have the field due to these guys. Now you're not satisfied with that. You want to find the field due to the entire wire. What do? You sum up all these fields. Okay? And summing is doing an integral. Okay? So in principle, this expression will let you calculate the field due to any current there. Okay? But of course, this integral would be impossible to do for this situation. For what situation can the integral be done?
Symmetric shapes.
Symmetric shapes, and we already gave you an answer. For an infinitely long straight wire, we gave you the answer. The field at this distance r is mu naught I divided by 2 pi r. Okay? All right, so that's the punchline of the chapter. Okay. So this current producing this magnetic field. All right, and this is known as the Biot-Savart law. Okay. All right, so that integral has been done for you for an infinitely long straight wire. And the magnetic field is mu naught I divided by 2 pi r, the distance, or a, the distance here from the wire. Yeah. What if here's the next symmetric current, a circular current? Okay. It turns out that for the circular current, you can't have an expression. You can have an expression for the magnetic field along the axes, and we'll give that to you in a second. But the field here, no luck. Okay. But you can pass a current, circular current like that in lab and measure the magnetic field here. And you can measure the field lines. And we'll do that, well, maybe we'll do that in lab. Anyway, so here are the field lines plotted. Here are the field lines plotted for a magnet, for a bar magnet. And you look, see, they're cousins. Okay? They're almost identical. The smaller they get more and more similar, the smaller the magnet. So what do you call this guy? An electromagnet. Okay? And this guy is very useful. Okay? Why is this useful? We've talked about this before. Turn on and off. Okay. The magnetic moment or the strength of the magnet is given by NIA. What is N? N is the number of turns of wires you have. I is the current. A is the area of the. Okay. You can change the strength of it on the fly. You can change the direction of it. Here it's north pole. You reverse the direction of the current and this becomes the north pole. Yeah? And when you don't want the magnet anymore, you can just turn off the current. Okay? So these guys are very useful. Like I said, so for a current loop, you can give the magnetic expression for the magnetic field along the axis. And here is the expression. Okay. R is the radius of the loop, and Z is the distance along the axis from the center of the loop. Okay. So the magnetic field strength is mu naught Ni R square, and I'll write this expression. Let me slightly. Ni will multiply pi R square, and so the denominator becomes 2 pi R square plus Z square to the power 3/2. Why did we do that? Well, okay, Ni area, this is this fellow here is mu, the magnetic moment, the strength of this magnet. Yep. And so mu naught mu divided by 2 pi. So this expression can be written as mu naught mu 2 pi R square plus Z square to the power of 3/2. What is this giving you? What is this giving you? It's giving you the strength of the magnetic field along the axis from this electromagnet, whose strength is mu. Well, what if you wanted the field at this point, at a non-axial point? Yeah, you're out of luck. Yeah. So what does that mean? That means this integral is hard to do. Okay? You can only do that for very, very symmetric situation and very specific locations. Okay? All right. So, and so what this says is, on next, what we'll show you is the following. If you're very far away, when Z is large, you can throw this guy away, and this becomes Z squared to the power 3/2, which is ZQ. And the expression will go as mu naught, mu naught mu 2 pi ZQ. And that's this expression, mu naught. Okay. Instead of Z, we've written X. So, okay. Here's, so the loop is like this, and X is the distance from the center of the loop. Yep. So there's the expression. And again, mu is the strength of the magnet. N is the number of loops in the coil, I is the current, and A is the area of the coil. Okay. All right, forget. What does moving charges produce? What does a current produce? Magnetic fields. Okay. How do you detect a magnetic field?
Moving charge particles.
You have moving charge particles. Okay. So, if you have a current in the presence of a magnetic field, that current will feel a force. All right. So let's combine the two. Okay. So here's a wire carrying a current. What does it do? It produces a magnetic field all around it. How do I detect that magnetic field? Well, I use a moving charge. This guy will feel a force from the magnetic field produced by this guy. Okay, so what we've learned is if you have two currents nearby, they'll apply a force on each other. And it turns out that if the currents are parallel to each other, they'll attract each other. And if the currents are in the opposite direction, they'll repel each other. Okay. I'll show you that in a second. But this expression tells you the force on the wires per unit length. Okay, is equal to mu naught times I1, I2 divided by 2 pi times the distance between the two. Okay, what will happen to the force if one of the currents is zero? Zero. Okay. Well, if one of the currents is zero, this guy is still producing a magnetic field, but you don't have moving charges to detect that magnetic field. Okay, so the force will be zero. All right, so now let's figure out this thing. Okay, the direction of the force. The force is on a moving charge is Q V cross B. Okay, so this current, you stick your thumb out in the direction of the current and it produces a magnetic field. Your fingers point in the direction of this magnetic field. So this current will produce a magnetic field into the plane of the paper. The direction of the field will be that. Okay, and now this guy tells you a positive charge moving in this direction, V cross B. V cross B will feel a force in the upward direction. Okay, so this current is exerting a force on these moving charges in the upward direction. Okay, well, these charges were a bunch of charges, and Newton's third law says this current will exert a force of that guy in this direction, equal and opposite forces, and the two guys attract each other. Okay, so parallel currents attract each other with the force given by force per unit length given by that expression. And anti-parallel currents repel each other. All right, let's make one more thing. Okay. These are for parallel currents, this expression. Is it valid now? No. So very specific locations, okay? Very specific configurations. Okay, this is Ampere's law. Let me remind you of Gauss's law that was related to charges. Gauss's law said the electric flux, which was given by a surface integral on a Gaussian surface. What is a Gaussian surface? So let's say you have a bunch of charges. Any enclosed surface is a Gaussian surface. And if you do this surface integral, that was equal to the charge inside divided by epsilon naught. So we're going to do the same thing. Well, we're going to give you a similar law for magnetic fields. This is the Ampere's law, except now, okay, so these currents are producing a magnetic field all around them. How far does the magnetic field extend to? Infinite. Yep. And again, if the current is like that, the fields are in a plane perpendicular, okay? Well, they're everywhere, but in the direction is like that. Okay, now what you do is you draw any curve and do this line integral. So let's say the magnetic field here is at that point, and there's this small element along the curve. Take this line integral along that loop, around that loop. And the value of that line integral is equal to the currents inside the loop. Mu naught times the total current inside the loop. Okay, so if you do and there's a sign to the current. If you're taking the line integral like that, you're always using your right hand. Okay. If the direction of the line integral is pointing like this, your thumb tells you that's a positive current, and this would be a negative current. You know? So if you're doing the line integral along that line, this is a positive current, and this would be a negative current. Okay. So this is the parallel of Gauss's law. Okay. So for instance, okay, so in this problem, in this diagram, this is currents coming out of the sheet, this is currents going into the sheet. Okay, so if you're going around the loop like this, these currents are positive, and the total current is 6 amps. If you take the line integral along this direction, these currents would be negative. That would be negative 6 amps. Okay. All right, so we're going to go around the loop, always go around counterclockwise. This will be positive, this will be negative. Okay, so if you did this line integral along this loop, going counterclockwise, the total current is 4 amps. The value of that integral would be mu naught times 4 amps along that. Along this loop, the total current is minus 1 amp. So it would be, the line integral would be mu naught times minus 1 amp. Okay? So. All right, now what we're interested in, so we saw that earlier we saw that if you have a long straight wire carrying a current I, what is the magnetic field at a distance R? Mu naught.
Mu naught I
Mm-hmm.
over 2 pi r.
2 pi r, okay. And how do you figure out the direction of the current? You use your right hand rule. Stick your thumb in the direction of the current, and your fingers point in the direction of the magnetic field. Okay. So if you're here, the magnetic field is there. Okay. All right, now what we want to do is, so this is outside the wire. Okay. Now the question is the following. Let's say we have a thick wire. Okay. And the current in this wire is evenly distributed, but there's a total current of I flowing. We want to know what is the magnetic field. We want to know what is the magnetic field inside and what's the magnetic field outside. Okay. Once you're outside, that's easy. That old expression will apply, and that's the distance R you measure. Okay. Now what you learn is if you're inside, only this current affects you. This current doesn't affect you. This is a common theme. If this was the Earth and you were here, only this guy attracts you. The force of this guy, the net force of this guy on you is 0. Okay? You saw that there. You saw this in charges. If you take charges and uniformly distribute them, when can you do this? Where can you?
An insulator.
Very good, my friend, very good. Okay, you take a bunch of charges and throw it on a conductor. What do? They go to the surface. Okay, so you take a styrofoam ball and evenly distribute the charge. The electric field at this point is only due to this guy. The electric field due to all these charges sums up to 0. Okay? So that's been a common theme, and that's what you'll see here. So if you have a thick wire and it's carrying a current like that, the magnetic field at this point is only due to this current. Okay? The magnetic field due to these currents will add up to 0. But we're not going to show any of the details. So there it is. Okay, so here's a thick wire. The current is coming at you. Okay, and again, to figure out the direction, all you do is stick your thumb in the direction of the current, and your fingers point in the direction of the magnetic field. At the center, the magnetic field is 0, and as you go further away, the magnetic field gets stronger and stronger. Okay, and the magnetic field will be strongest on the surface. And then once you are out of the surface, it falls off as 1 over distance. Okay, and that's what this is showing you. And so this is the strength of the magnetic field. R is the radius of the wire. Capital R is the radius. Okay, till you get to the surface, the magnitude of the magnetic field increases, and then once you are out of the surface, it's falling off as 1 over R. Okay. So for R greater than R, here's that old expression. I naught is the current through that entire wire, total wire. Okay. And inside the wire, the current is, magnetic field is 0 at the center, and that increases linearly till you get to the surface. Okay. All right. So you saw a long wire producing magnetic fields which are concentric circles. Okay. Now, here's another configuration. Let's say you wanted to produce magnetic fields inside a donut. Okay. Strong magnetic field inside a donut. What you can do is wrap the donut around with wires, and now you'll have field lines that are circular like that. Okay, the field are strong. The field is strongest here and weakest there. But if the thickness of the donut is small compared to the radius, then you can think of the field as uniform. Okay, so if the donut is very large and thin, then the field inside is essentially uniform. Okay. Why do you think we might need to produce a field like this? We talked about it. Very good. Okay, so remember, charged particles get trapped around field lines, and if you have a really hot gas and you don't want it hitting the wall, and it can just get trapped by the line and go around in circles and never hit any wall. Okay. And so what happens is, so this guy is trapped around this line. This positive charge is going in this circle, and this positive charge is going in this circle. And when this guy meets him, they collide, they could fuse together. Okay? All right. We saw okay, so here's the donut, there's the field inside, and there's the particles trapped around that concentric field. Okay. So there's the, okay. Okay, so those are the field lines, you can think of them. Okay. So there are situations when we need to produce magnetic fields like that. And so the magnetic field strength, like I said, well, it's strongest here and weakest there, but here's the expression for the magnetic field, mu naught n. N is the number of turns per meter. Okay, so 2 pi r, that's the length of the toroid. 2 pi r is the circumference of the toroid, and the total number of turns divided by that gives you the number of turns per unit length. Okay. And I is the current. Okay, so you want to produce a stronger and stronger field. So the stronger and stronger field, the hotter the gas can be without hitting the walls. Okay. And so to produce stronger and stronger field, you would need to increase the number of turns per meter and increase the currents. Okay, increasing the number of turns, you know how to do it. You just wind more and more wire. What can you do to increase the current? You take an ordinary wire, you heat, pass too much current, a bunch of it turns into heat.
You see, we got in one.
All right. So a solenoid. So take a cylinder and just wrap wire around it. That's a solenoid. And if you pass current through it, what it does is in the cavity of the solenoid, it produces a uniform field. Okay. There's the field. And the expression is the same, mu naught n. N is the number of turns of wire per unit length, and I is the current. Okay. So we need this kind of fields in a particle accelerator. Okay. So there's the solenoid, and inside there is that uniform field that we talked about. So here are the detectors, CMS, Atlas, Alice, and all those. That's where the detectors are. You go to UF, go to the basement in physics, and you can see this there. So inside this is a solenoid. You have a strong magnetic field inside like this. Okay? And this thing is packed with detectors. Okay, so beams are coming and colliding. So here's the solenoid. Beams of protons are coming and colliding there, and that energy is converted to particles, and that magnetic field will curve the particle. And the more mass of the particle, the smaller the curvature. Okay? So from the curvature of the particle, from the curvature of the tracks, you can tell what is the mass of the particle. So this thing is packed with detectors, and UF does that, so you guys can go check it out. So here's for a proton-proton collider. Here's for a gold-gold nucleus collision. That's a mess. But they track every particle. And nowadays they get so much data, I think they're able to analyze only 1 or 2% of the data. Something like that. All right, so what we saw was there are situations when you want to produce fields like this. And there are situations where you want to produce fields like that. Okay, so you saw that this is needed in a fusion reactor, this is needed in particle accelerators, and so on. Look at that, that's huge. Look at the size of it. All right, what are we saying in this chapter? Moving charges produce magnetic field. Yeah, yeah. All right. I knew what you meant. All right, so you have charges moving in atoms. You have electrons moving in atoms. Okay, so they ought to produce magnetic fields. So, and so this is a sort of a classical and quantum mechanics mixed together, so semi-classical picture. All right, so here's an electron going around. When an electron goes around like that, it's really a current going in this direction, okay, in the opposite direction. And a circular current behaves like a magnet, and here's the strength of the magnet, okay. And the strength of the magnet is I times A. I is the current, and A is the area of the loop, okay. Now it turns out that the orbital motion of the electron is quantized. The electron cannot go at any speed at any distance inside an atom. Okay, it can only take specific orbits, and the angular momentum, orbital angular momentum, MVR, is only NH bar. Okay, so this is the unit in which it's quantized, n being an integer. Okay, again, don't worry about all of this. In chemistry classes, when you learn that the orbital is 1s, 2s, 3s, and so on, that n is the 1, 2, 3. Okay, so 1s, 2s, 2p, 2p, 3s, 3s, 3p, 3d orbitals. Okay, the 1, 2, and 3 are the n's. These are the L values. Okay. Anyway, so I times A, which is E times and related to the orbital angular momentum L, and this is quantized, and this can only take these values. And L equal to 0 is what's called S in chemistry. L equal to 1 is P. L equal to 2 is D orbitals, and so on. Yep. L can only go from 0 to n minus 1. Okay, so for n equal to 1, L can only be 0, which is, so you can only have one s orbital. You can't have one p orbital because L can't take values of 1. Okay. All right. So in an atom, the electron going around produces a magnetic field, and that's the magnetic moment of the electron going out in an orbit. Okay. In an atom, each electron circles the nuclei once in about 10 to the minus 16 seconds. So the electrons are going pretty fast. This would produce a current of 1.6 milliamp. A single electron is producing. And a magnetic field of about 20 Tesla at the center of the circular path. So the magnetic field the electron produces is 20 Tesla, a single electron. You saw what happens in an MRI machine. What is the MRI machine magnetic field strength?
7, like 1 to 3.
Yeah, 1 to 3 Tesla. And you saw it can throw a gurney across the room. Okay. your body is full of carbon atoms, which has 6 electrons running around. 6 times 20, 120 Tesla. So what's going on? I mean, it should produce, huh?
They cancel out.
So for every electron going like that, there's an electron going like this. Okay. So, and if you have a odd number of electrons, the last electron is in an s orbital, which is sort of going like this and not producing any magnetic. Okay. Again, that's just giving you. That's not the precise language, but that's roughly what's going on. Okay. So, in most materials, because of oppositely moving electrons, magnetic effects produced by orbital motion is zero. Okay, essentially. Electrons spin as well. Any motion of a charge produces a magnetic field. So the spin motion also has a magnetic effect, and because of the spin motion here, the electron is acting like a magnet like this. And that's the strength of the magnet, and it's named in honor of Mr. Niels Bohr. It's called the Bohr magneton. Okay. And it's E times h bar divided by 2 times mass of the electron. The proton similarly is spinning. Okay. And since the proton is positive, its magnetic moment points in the same direction as the spin, okay, as the angular moment or the spin momentum. The proton mass is 2,000 times the mass of the electron. So this magnet, even though the charge is the same, this magnet is 2,000 times weaker than that, roughly, all right? So, but in NMR, this is the magnet you target, not this target, not the electron's moment. Okay. All right. So, and see, the strength of the magnetic moment of the electron spin is given by that. All right. So here's the magnetic moment of these atoms. For the hydrogen atom, you see it's exactly that. That's the moment of the spin. Okay, well, what's going on? So the hydrogen atom, there's the hydrogen atom. Okay, what all magnets do you have here? You have the magnet of the proton, but this thing is 2,000 times weaker than that, so you can ignore this. The orbit is 1s. So in the s orbital, s is L equal to 0. So that has no magnetic moment. Okay, the orbital moment is 0. Okay, and then the only thing left is the electron moment, and that's what that is. Okay. So for the hydrogen atom, the magnetism is coming from the spin of the electron. Okay. What about helium?
2 electrons cancel each other out.
Very good. When that spin is pointing up, the spin of the other guy is pointing up. Okay. Same thing for neon. For all the noble gases, okay, they're not reactive and they're not magnetic. Yep. This thing is almost twice that. So it has 2 electrons, unpaired electrons with their spin pointing in the same direction. This is, it probably includes orbital angular momentum. Okay. So now we'll talk about magnetism. Magnetic materials, you will, as engineers, you'll be using magnetic materials for various things. Okay. So based on magnetism, you classify material as paramagnetic, ferromagnetic, antiferromagnetic, or diamagnetic. and ferrimagnetism. So we'll mainly talk about these three. For paramagnetic and ferromagnetic material, their atoms have permanent magnetism. Okay, hydrogen atom has a magnet. Okay, neon and argon, they don't have magnetism. None of the noble gases. Okay, for these materials, their atoms are magnetic. So what is the difference between them? The difference between them is these atoms do not interact very weakly with each other. These atoms, their magnetism interacts strongly with each other, and the neighbors are all lined up. Okay, so for ferromagnetic materials, all the magnetic moments are lined up. So for instance, look at this. This is a ferromagnetic material. That's the size of a grain of sand. In this size of grain of sand, there's about 10 to the 20 atoms, and all those guys are lined up in the same direction. So if you had just that little piece, that would be a strong magnet. Except that, when you go out and dig up a rock, you get a big piece of rock. Well, can we make this into a strong magnet? Can we line all the domains up?
If you apply a strong enough magnetic field.
So, yeah. So if you pass a current, make it into a cylinder, pass a current, and these guys would line up like that. So you can make a strong magnet. Okay. So there are soft magnetic materials, okay, which you apply this current and they'll line up, and you remove the current, they'll go back to the random shape. So they'll lose their magnet. And that's useful because you can pass a current like this, have them line up, then pass a current in the opposite direction, have them line up in the opposite direction. Okay. And so you can change the orientation of the magnet as needed. Okay. So paramagnetic and ferromagnetic materials have atoms with permanent magnetic moments. Diamagnetic materials are those made of atoms that do not have a permanent magnetic moment. Okay, and when you introduce them in a magnetic field, what they'll do is they will so if you bring a magnet near a diamagnetic material, what they'll induce is they'll induce a magnetism in the opposite direction in their atoms. Okay, so that's what happens for diamagnetic materials. So, okay, we'll come back to this in a second. Okay, so here, paramagnetic substances have small positive magnetic susceptibility. Okay. Okay, so diamagnetism. A diamagnetic substance is one whose atoms have no permanent magnetic dipole moment. When an external magnetic field is applied to the diamagnetic substance, such as bismuth or silver, or water as well, water is diamagnetic, a weak magnetic dipole moment is induced in the direction opposite to the applied field. Okay, so if you have a diamagnetic material, you bring a magnet close by, you will induce a moment in the opposite direction. So what this is showing us is this is a frog frozen, so he doesn't run away and wiggle. You bring a magnet like that. What is a frog? It's mostly water. It's a package of water. And this becomes a magnet like this. And it's floating. So this is a frog that's been levitated. And apparently, so in the book, he'll say, after the experiment, they unthawed the frog and he ran away. So, yep. A superconductor is a perfect diamagnet. Okay, so here is a material that becomes superconducting. At temperatures higher than its critical temperature, it's a normal metal or insulator or whatever it is. You decrease its temperature below the critical temperature, it's become superconducting, and you see it has expelled this magnetic field. So what has happened inside, so if the magnetic field was like that, inside it has produced a opposing magnetic field canceling the external field. Okay. So if a permanent magnet is brought near a superconductor, the two objects will repel each other. And you've seen this sort of stuff is used in maglev trains. Okay, so the track is magnetized, and we saw a video of that. And you put a superconductor in the maglev train, okay, and it'll float, and you can have the train off the tracks, and friction is eliminated, and you can move the train easily. Okay. That's the idea. I believe Shanghai Airport has the longest running maglev train from the airport to the town, 40 kilometers. The peak speed is 250 miles an hour. So it speeds up and then slows down. All right, guys.